This is pre-AP, pre-calculus. This is note section 5.3, discontinuities of rational functions, an analytical approach. There are two major types of discontinuities in functions. Remember that discontinuities come when the good old denominator is set equal to 0. Now, sometimes there is a factor in the denominator that cancels. And sometimes there's a factor in the denominator that does cancel. I'm sorry, that does not cancel. Keep in mind these are both referring to denominators. If the factor cancels, that is known as a removable discontinuity. If the factor does not cancel, it's known as a non-removable. Removable discontinuities, those are called point discontinuities, and that happens when there is a hole in the graph. Non-removable discontinuities come in two varieties. Infinite, that's when there is a vertical asymptote, and jump discontinuity, and that can occur, doesn't have to, but can occur in a piecewise function. Not every piecewise function has a jump discontinuity. So once again, two types of discontinuities, removable and non-removable. Removable is point discontinuity, there's a hole in the graph. Non-removable could be infinite or jump. Infinite vertical asymptote. Jump is, I haven't explained what it is, but that can occur when you have a piecewise function. So what's the description of a graph for a removable point discontinuity? Two pieces that connect at an open circle because each piece approaches the same y value. When we say approaches, that's implying a limit. If we were to approach the x value where this hole is, the limit from the right and the left would be approaching the same number. For a vertical asymptote, the description of the graph, two pieces that do not connect because they approach infinity or negative infinity. If they approach infinity or negative infinity, that means they're going up or down forever as they get closer to this x value. And that's what a vertical asymptote is. Jump discontinuity, what does that look like? Two pieces that do not connect because they approach different y values. Once again, the word approach, that's a limit. As you approach the x value from the left, the limit is a number. As you approach from the right, the limit is a different number. This middle one here, the vertical asymptotes, as you approach x from the left or right, the limit is approaching infinity or negative infinity. Moving down, the graph below has a removable point discontinuity at x equals 1. Now that's being redundant. If it's removable, it's point discontinuity. It means there's a hole in the graph. So if you look here, if we follow the description we have up above, if we approach x equals 1 from the left, y is approaching 1. If we approach from the right, it's also approaching 1. But there is a missing point at 1. The domain for this is negative infinity to 1 in union with 1 to infinity. What is the range? Well, the range starts at negative infinity and it goes up. It's true there's a hole here at 1, but there is a y value here of 1. Every y value is accounted for. So the range is negative infinity to positive infinity. It's not for every graph that has point discontinuity, but it is for this one. The next one, the graph below has a non-removable infinite discontinuity at x equals 1. The limit as x approaches 1 from the left is positive infinity. The limit as x approaches 1 from the right is negative infinity. That's what a vertical asymptote is. This is infinite discontinuity. The domain for this, same as it was here. X goes from negative infinity to 1 and from 1 to infinity. The range for this is also the same as it was here, because every y value is accounted for from negative infinity to infinity. Third graph, this is a piecewise function. If we approach 1 from the left, y is getting closer to 1. If we approach 1 from the right, y is getting closer to 4. Those are different y values. That's what the definition of jump discontinuity is. The domain for this, well, all x values are accounted for as you go left to right. We're missing an x value of 1 here, but it picks it up again right here. So this domain is all real numbers. The range is also all real numbers, because if you start from the bottom and go up, every y value is accounted for as we continue through this graph. Nothing is missing. On the flip side, for each of the indicated graphical properties, find each of the indicated graphical properties. A, values of the zeros. B, coordinates of the y-intercept. C, equations of the vertical asymptotes. D, coordinates of any holes. Coordinates of any holes are the ones that are going to give us the most trouble. Just judging on previous experience, that's going to be the most difficult one for us. If a function does not have a particular property, explain why it does not. Show your work. Now this says show your work, or you can explain. I'm going to show my work for some, and I'm going to explain for some others. So first of all, we would likely want to factor this, because this is often easier done when it's factored. The numerator factors into a 2x plus 1 and an x minus 3. The denominator factors into an x plus 2 and an x minus 3. So let's talk through some of the stuff that's happening here. 1, the y-intercept. The y-intercept is found by taking the ratio of the coefficients. That's part B. I'll just put that right here. B, the y-intercept is negative 3 over negative 6, which is 1/2. I might have said the word coefficients earlier. I meant constant if I said that. So the y-intercept for this is the ordered pair 0, 1/2. Part A asks for the value of the zeros. The 0 comes from a non-canceling factor in the numerator, and the only non-canceling factor in the numerator is 2x plus 1, which means that x is going to be negative 1/2. So a 0 at x equals negative 1/2. Vertical asymptotes, that's part C. Vertical asymptotes happen from non-canceling factors in the denominator. So that's at -2. Vertical asymptote at x equals -2. We have D, coordinates of any holes. Holes happen from canceling factors from the numerator and denominator. And the one factor that would cancel for this is x minus 3. Set it equal to 0, and we get there's a hole at x equals 3. Now we need the y value that goes with this. Coordinates of a hole is an x value and a y value. So we have the x value, and remember I said this is going to be the hardest one for you folks. So we have a hole at 3. We don't know what the y value is. Now if we plug a 3 back into this function, it's going to be undefined. So you have to plug it in after you've canceled factors. So this is going to be f of x equals, if you cancel the factors, we get 2x plus 1 and x plus 2. If you plug a 3 into this, we're going to have 2 times 3 plus 1 over 3 plus 2. That's going to give us 6 plus 1 over 5. It's going to give us 7/5 is f of 3. Let me organize this a little bit better because right now it's not so great. So we have a hole at the ordered pair 3 7/5. Let me make this a little bit smaller. Oh, Picklesworth. Now, all that is a lot to remember. So there's one thing I didn't do yet that I really need to do, and I'm going to do that in this space right here. And generally, you would do what's going to go in this space first, okay? So I didn't organize this in a very good way. Looking back to the original factored version, factors that cancel produce holes. So there's a hole at x equals 3. A factor in the denominator that does not cancel, that's a vertical asymptote. There's a vertical asymptote at x equals -2. Factor in the numerator that does not cancel, that's a 0. So this has a 0 at x equals -1/2. We can get all that stuff directly from that equation. When the x minus 3's cancel, this is the part that I didn't write down. You write down the function from what's left, and you can't just leave it like this. If you leave it like this, you are suggesting that this is equivalent to this. And it isn't, because we had this extra factor in the top and the bottom. So how do you fix it? Simply put a comma, and you either say, oh, by the way, there's a hole at 3 7/5. That fixes it. Or you could say, comma, x cannot be 3. By saying x can't be 3, that's implying that there must have been an x minus 3 in this problem in the top and bottom, and that's why it cancels. Let's see, if a function does not have a particular property, explain why it doesn't, show your work. All right, we're finished with that problem. We're going to do the next one without showing all that work. We're going to explain instead. Explaining, oh geez, I'm making a mockery of this. Explaining might be better. All right, let's check out, well, before we check the next one out, let's just confirm. Let's look at our graph here. So all this stuff makes sense. We have a 0 at -1/2. That's what it says right here. Look, we get a 0 at -1/2. We have a y-intercept of +1/2. We have a positive y-intercept +1/2. We have a vertical asymptote at -2. Look, our graph has a vertical asymptote at -2. We have a hole at 3 7/5. We have a hole at 3. And this could be 7/5. Bravo. Number 2. We'll do this one once again by explaining instead of showing all of our work. So let's factor this. The top's going to factor into an x plus 3 and an x plus 1. The denominator is going to factor into an x plus 3 and an x minus 1. This is going to give us a new function, g of x equals, now keep in mind these x plus 3's cancel. When they cancel, what happens? That means there's a hole at x equals -3. So I can rewrite this function g as x plus 1 over x minus 1, and then put a comma and say we're going to have a hole at -3 something. I don't know what that something is yet. I'm not going to leave that blank. But so what else do we know? We know that x minus 1 is going to be used to find a vertical asymptote at x equals 1. X plus 1 is going to be used to find a 0 at x equals -1. If we divide the constants on the top and bottom, that's going to give us that we have a y-intercept of -1, because 3 divided by -3 is -1. Cool? Now let's show some work for some of this stuff or explain. So part A, zeros. So instead of doing work, I'm going to say g of x has a non-canceling factor of x plus 1 in the numerator. Therefore, g of x has a 0 at x equals -1. Done. B was asking for the y-intercept. So we could say the ratio of the constants of g of x in the numerator and denominator is 3 to -3. Conclusion, g of x has a y-intercept at 0, 1, because 0, -1, because 3 divided by -3 is -1. C, we're supposed to find the vertical asymptote. G of x has a non-canceling factor of x minus 1 in the denominator Therefore, g of x has a vertical asymptote at x equals 1. Part D, it's about the whole. Running out of space here, aren't I? D, g of x has a canceling factor of x plus 3. Conclusion, g of x has a whole at x equals -3. Now we still need to show work to figure out what the y value is of this. So I take g of -3 which is negative 3 plus 1 over negative 3 minus 1, and I get negative 2 over negative 4, which is 1/2. Once I know that's 1/2, I can put that up here in this blank spot that I had up earlier. So this is what we're graphing. For number 2, we didn't show our work, we explained. If it was a free response question and it asked you to explain, this is how you would explain it. Let's look at the graph and see if this stuff is all checking out the way that we were hoping it would. So this says there's a hole at negative 3 1/2, it looks like. We're saying negative 3 1/2. That checks out. Looks like there's a vertical asymptote at x equals 1. We have that there's a vertical asymptote at x equals 1. It crosses the y-axis at negative 1, crosses the y-axis at negative 1. Am I missing anything else? Vertical asymptote. I think I'd mentioned all the things. Anyhow, it all checks out. The only thing we don't know how to find yet is the horizontal asymptote, but that day will come. It will come. All right, number 3. I'm going to show my work for this because it seems like it's a lot less writing. Factor. The bottom factors into an x plus 2 and an x plus 3. So what do we know? We know this is going to have a y-intercept at 2, 6, which is 1/3. We know this is going to have a hole at x equals negative 2, because those are canceling factors. There's no factor left on the top, so there is no 0 for this. And this has a vertical asymptote at x equals negative 3. That's a non-canceling factor in the denominator. Write down what h of x is equal to once you've canceled out. There's nothing left on top. There's a 1. We have a factor of x plus 3 on the bottom. Oh, by the way, there's a hole at negative 2 something. We got to figure out what that something is. Part A, zeros. We do have to explain because it says if a function does not have a particular property, explain why it does not. So h of x has no 0 because there is no, there's a lot of double negatives here. There is no non-canceling factor in the numerator. I was going to get away with not explaining for this one, but I'm going to have to. B, the y-intercept. I don't need to explain this one. The y-intercept is going to equal 2 over 6, which is 1/3. Therefore, the y-intercept is 0, 1/3. Part C, this is the vertical asymptote. Vertical asymptote is going to be x plus 3 equals 0. So x equals negative 3. That part's done. Hole. The hole, we take the canceling factor and set it equal to 0. And we solve it. We get there's an x value of negative 2. To find the y value, see if I can use my space better than I did last time. To find the y value, take what's left of the function, replace the x values with negative 2, and we're going to get 1 over 1, which is 1. The location of this hole should be negative 2, 1. We answered all the questions. Let's just look at the graph and see if everything is making sense. That has no zeros. Well, does this graph ever touch the x-axis? No, that checks out. Y-intercept is 1/3. This looks like it could be 1/3. Vertical asymptote at negative 3. You betcha. Hole's coordinates are negative 2, 1. Should write that down someplace. hole's coordinates, -2, 1. That all checks out. So one left to do. Do this one on your own. And then after you do it on your own, pause the video, do it on your own, then come back to this and see what's here. And while you're doing that, I'm going to find my key for this, and I'm going to bring it up. It would look like this. That's how your work could look for this. All right, once you confirmed that you've done things correct, go ahead and start on your homework. If you didn't do things correct and you need help, good golly, Miss Molly, let me know. And peace in the Middle East.